presentation was continuation of the structural analysis of Aesop's The Tortoise and the Hare. You can hear? You can hear good? So at first we started off with what we went over in class yesterday where... It's on. Where the tortoise and the hare decide to have a race, and then at first they set up the parameters of the race saying that they're going to run a certain distance, and then ultimately who finishes first would be the winner. And where we left off, we left off when the race began, where the hare is ahead at first, and this is the early iteration stage, so like the early process in the test that a material would go through. And it starts off with the hare being overconfident and takes a nap halfway through. So the initial performance doesn't always necessarily compare to the overall performance. And then the hare takes a nap and oversleeps, and the tortoise has an opportunity to pass the hare. So you need to understand the relevant performance metric being tested, because if it was a sprint, the hare would have won, but because it was a long distance race, the tortoise won. And ultimately, in this first part, the tortoise beats the hare, which means that based on your initial assumptions and testing, that the initial strongest may not always be the expected outcome.
So this is sort of just continuing off of what she said. So the hare went quickly ahead, so that the solution process runs quicker for the first element that we're studying initially. Then the hare stops and falls asleep, so the solution process fails for the first element. And then the tortoise passes by, wins the race, and so the solution process completes for the second element only. For part 2 of the race, we have new initial conditions. The hare realizes that he was overconfident, so you analyze the shortcomings of the previous solution process. He then challenges the tortoise to another race, and after this they agree on the same route as before, so they have the same initial guess for the iteration process. They start racing, and they run the adapted solution process. Here the hare runs fast and consistent across the entire route, and so the solution process runs well for element 1, and the hare ends up winning by several miles. So the solution process completes for element 1, but doesn't complete for element 2.
Okay, so part 3, basically, after part 2, the hare won due to the new initial conditions stated. The tortoise realized he couldn't win the race as currently constructed, so he had to reiterate on what were his shortcomings in the previous process. The tortoise then challenges the hare to another race. He wanted to see how his time would vary based on new conditions, and they agreed to change the route. So this creates a new initial conditions and guesses to iterate. So from there, they start racing. They try that new solution process. The hare runs ahead of the tortoise, but runs into the river because he wasn't prepared. But the solution process runs well for the first element, but then they encounter a point where there might be failure. The tortoise catches up, swims through the river, and he ends up winning. So this basically shows how so the tortoise's solution process completes for this specific iteration, but fails for the hare.
So after this one, where the tortoise wins, we have another trial where they decide to vary the course yet again. They agree on the same route, which is the same initial guess for both variables being tested. And they start racing together ultimately, and they decide that even though they both have their strengths in certain scenarios, it's better to work together, where one would take over a part where it has the strength, and then the other one would take over a different part. So initially the hare carries the tortoise because he's faster on land, But when they get to the river, where only the tortoise can cross, the tortoise decides to carry the hare across the river. This shows that both elements working together can lead to both element 1 and element 2 ultimately leading to success by working in combination. And then once they get back on land, the hare carries the tortoise again, and then they finish the line. They cross the finishing line together.
So over here, there was like a slide before that. Yeah, here it is. Okay, so when I interpreted the story, I saw it as an allegory for material testing. So specifically when it comes to testing what happens to a material when it's put under stress, and how much strain can be used on that material. So, for example, in this allegory, we can see that the hare is the brittle material, while a tortoise is a plastic material. And the amount of strain can be thought of as the distance ran within the race. Because strain is just like the amount of deformation happening, so that length could be the distance ran during the race. And in this metaphor, the Young's modulus, the initial slope of the graph, shows how fast the racer was initially going. Next. So with this allegory, you can see that the hare is ahead at first because brittle materials have a generally like higher Young's modulus that caused like the higher, steeper slope within the graph shown before. The hare is overconfident and takes a nap. So basically, this shows that the brittle material reaches like a fracture point, and it stops, right? It stops responding, like creating more strain and going the distance that it needs to go. He takes a literal break. He oversleeps, the tortoise passes him. This basically shows that while the brittle material broke, the plastic material continues enduring the strain or the distance that's going through the rest of the race. And then lastly, the tortoise beats the hare. This is because through continual endurance, the plastic material strains more, elongates more under a continual amount of stress, and it's able to complete the distance that it was assigned to go. So, yeah.
Thank you so much. Very interesting, different kind of thoughts you gave to this to get into the allegory. Really appreciate that. As I said, there are no unique ways of interpreting it. Each of us can do that in different ways. Just playing the devil's advocate in terms of the choice of one being plastic, the other being brittle. If you look at the actual structure of a hare or a rabbit for that matter, it's typically more softer.
That's true, yeah.
Compared to the tortoise, which is a harder shell.
Yeah.
So how would you try to counteract that argument?
I say that this is a literary metaphor. I'm not interpreting it like literally that like obviously the hare, the tortoise would be made out of a more hard, brittle material. It's probably more equivalent to like ceramics in that way, you know. And like generally the hare would be a little bit more aerodynamic. But I don't know, as like a metaphor sense, I feel like it works though. Yeah, because it's like a metaphor for how it goes the distance. Yeah.
And this may not have anything to do with structural analysis, but more from the point of view of the aerodynamic shapes.
Yeah.
And also the fact that one of them goes through the water, so the hydrodynamic shape as well.
Yeah.
So would you like to comment anything on that?
I mean, hares aren't really meant to like swim in water, are they?
Right.
Yeah. So like maybe like one has better properties to work on land and another has better properties to work on like in sea. And because of that, like I really like I think the slide like part 4 where they work together and they combine their strengths. and to like solve like the race problem, I guess. I really like that part because it shows how different things can be combined to better accomplish a goal.
Absolutely, absolutely. Yeah. That's the biggest takeaway.
Yeah.
Definitely, when we talk about that. No, what I was trying to get to is there's a difference between something being hydrodynamic and aerodynamic, really more efficient in terms of the shaping. For example, the shape of a ship is very different from the shape of an aeroplane. So from that point of view, can you come up with some points in terms of what's the typical difference and why so, if you can think?
I think the tortoise having the shell of sorts where it's flat on the bottom and then curved on the top, it allows it like its own center of gravity to be very close to the bottom of the shell, and also like this flat surface, even though it's not aligned with how boats are structured. Even though it's not aligned with like how boats are made with I forgot what it's called, but the structure that continues under the water to keep it afloat. I think it works in this sense because a tortoise is small enough that it can rely on buoyancy to get itself across, whereas a hare is meant for springing and like springing off a hard surface with like its muscle composition, its structure, and the way that its legs are shaped. So being able to spring off a ground is what makes it able to be faster than a tortoise on land, at least.
Excellent. Because these things are also important because there's a lot of funding and research going on around the world, both in academia and industry, in terms of bio-inspired materials and bio-inspired structures and things like that. So, because nature has evolved these beings for millennia, whereas aerospace structures have been around for just a little over a century. So, a lot to learn from them, but you can't blindly copy. But a question of trying to take it forward in a more thoughtful way, more of an adaptation rather than a copy of plagiarism.
Yeah, I think this also works in the sense of this metaphor too, because the hare was able to do it because of the way it was built on land, and then the tortoise had the properties to go in water. And in terms of like materials and structures, we have composites where it tries to take the best elements of two things and sort of combine it to meet in the middle, where it would be stronger than each individually. So like, I don't know, if we take like a frog, for example, like it sort of has the same leg structure as a hare, so it's able to spring on land, but it also is closely related to like tortoises as being both aquatic and land animals.
Taking it even a little forward, there's a lot of interest, as you know, from NASA and other space organizations in terms of planetary exploration and land rovers, so robots which are walking on the land to test that and things like that. So any takeaways from this story for them?
I mean, I think like the biggest thing from the story is like adaptability and stuff like that. So when you're like, say you're on Mars, that's like a different surface, different gravity, different like it's a different landscape than what we are used to. So being able to combine things on Earth that might be able to simulate what's happening in like a Mars landscape, like the desert, like it's kind of like deserty, right? Being able to like artificially simulate like the gravitational circumstances on Mars might be like a way that we can like see how we can combine what we know from Earth and also adapt it to Martian explorations.
Excellent. Thank you so much. So I'll come up with my interpretation of this story in the next class. We just wanted to cover certain things which will be of relevance to that interpretation. So I'm going to be mostly focusing on that today. Some of these ideas also came up in your presentation itself today. In terms of the distinguishing features, like it's on? Yeah? Okay, fine. So in terms of the distinguishing features of structures which are used in the flight vehicles, all kinds of flight vehicles, all the way from rockets and satellites to helicopters and aircraft, compared to any other structures that you have, which are engineering structures like what you see in this building itself in terms of beams and columns, etc., or even the floors and ceilings. So we want to see what kind of primary differences are there. So structure itself, as you know, briefly we mentioned this last time, has two aspects to it. One is the geometry and the other is the material. And so whenever we say, because this course is titled Structural Analysis, whenever we are talking about structural analysis, analysis, as I already said, opposite to synthesis, you're trying to break apart and look at things, how they are going to be useful for a particular application. Similarly, in terms of the structure also, when you're designing a structure for an aerospace vehicle or any other engineering structure, there are two decisions that you have to take. What is going to be the shape and the sizing of that? And then the other would be in terms of the choice of a material or a set of materials and where you put each one of them and how you combine them. So some of those points were brought up by you in terms of the suitability of element 1 and element 2 in various applications and how you try to bridge them together. So before we get to specific materials, I know you had a course on materials itself earlier, right? So did you in the previous? Yeah. So it'll be more of a brushing up or review of that. Did you cover any amount of composites on that? Yeah. Okay. Good. So so we will be brushing through some of those things in terms of how they are relevant towards the analysis of those structures made out of composites, and as opposed to most aerospace structures which were made out of, let's say, aluminum alloys and such other lighter alloys in the earlier days. Not that they're already out of competition, it's just that they're used along with composites, and slowly the percentage of composites being used on most similar class of aircraft is increasing every generation of aircraft. So that being the case, I would like to listen from you in terms of what are the typical differences that you have between flight vehicle structures and anything. Of course, during your talk, at the end of your talk, we talked about ships and things like that, which are also moving structures, but moving in a different medium. Instead of air or space, they're moving in water or any other, or land, as in the case of the Hare. But more particularly, if they're static and not at all moving, as in civilian structures like this building or a bridge, then we would like to see from both those aspects which I just mentioned, that a structure consists of its geometry and the material. What are the distinguishing factors? So we will start, first of all, let's say with the geometry, in terms of the geometries that are typically observed in civilian engineering structures as opposed to aerospace structures. So can you point out any? Yeah, good point. Yeah. Anybody else? Yeah. Excellent. Yeah, I'm really glad you brought that point when I'm asking about distinguishing factors, that there are a lot of similarities as well, which is very important to notice that at the end of the day, we're all applying the physics and math that we learned in various different to meet various requirements coming from the actual application at hand, right? So there are going to be certain similarities, there are going to be certain distinguishing factors. The main thing, of course, is in one case it's moving, in the other case it's not moving, and the kind of forces that come when it is moving. By forces, we mean in a more generalized sense, it could include moments as well. So they are slightly different, and how they change with time, how they change with the motion are very different from how the loads act on this and how they change as well. So, and also the environment in which they operate. So you have an environment which is changing continuously as the aircraft flies. In the case of a rocket, for example, it might be beyond the atmosphere as well. So part of its flight is through the atmosphere, and the remaining portion is in space. So entirely different kind of an environmental condition. So the question of adaptability, which is also something that some of you brought about during the analogy that we had with the hare and the tortoise story, so the allegory, right? So all of that we will try to consider one by one now. So how many of you had a chance to go visit this building on campus? You did? Okay, good. So, so a structure like this is typical civilian engineering structure. A solar-powered aircraft like this is something that you have on the other end of the spectrum, a long endurance or medium endurance kind of high altitude kind of aircraft which fly for a very long period of time. But irrespective of what kind of flying vehicle it is or what kind of civilian structure it is, a primary difference is in the choice of the material. The material choices, as you said, you had gone through a course where you learned composites. Very rarely would an initial undergrad course on civil engineering structures deal with composites. The primary reason is that these have much lower density, but at the same time offer a large strength or stiffness, which is, in a sense, you're talking of not absolute strengths and stiffnesses anymore, but a relative strength and stiffness compared to its mass density. So what we call as a specific strength or a specific stiffness becomes more critical than the absolute strength or absolute stiffness. What do we mean by specific strength or specific stiffness? It's the same strength or stiffness divided by the mass density of that particular material. The higher it is, it becomes more suitable for aerospace application. But of course, that's only one of the requirements, a very primary requirement, but nonetheless, there could be many other requirements as well, and some of them could conflict with this, and that's where the decision-making process in a design comes up, and we need to be aware of that. So this is what we meant by specific strength and specific stiffness. So for example, if you have, in the case of a metal, you typically have the yield strength sigma y or the ultimate strength sigma u. If you divide that by rho, which is a typical symbol used for the density, then you get a sigma u by rho, which is the specific ultimate strength. Similarly, if you have the Young's modulus E of a particular material, isotropic material as single E, then you have that E divided by rho becomes the specific stiffness that we are interested in. So, whereas in a civil engineering structure, we are predominantly comparing with two materials, apart from the economy and things like that, in terms of purely load-bearing capabilities, the choice of the material depends upon the one which has a larger sigma u or a larger sigma y, which is why you find a lot of steel being used in many of the civil engineering constructions, because it has large absolute moduli. Though its specific strength or stiffness may not be as good as some of the other candidate materials, right? So the next thing is what Aryek brought about in terms of the aerodynamics, right? So the external shape of the structure. So in the external shape of this need not have the smooth surfaces and things like that, whereas here the airfoil cross section has to be fairly smooth, except at the trailing edge, which is sharp. The leading edge has to be kind of rounded and things like that. So there is a certain external shape which is dictated by non-structural consideration. Aerodynamics is a non-structural consideration. Example non-structural consideration. There could be other non-structural considerations as well. Can you think of any other than aerodynamics? Yeah. Come again? Yeah, absolutely, yeah. Sure. No, but from dictating the external shape, yeah. So your choice would also be important because shaping requires certain manufacturing techniques, and shaping it in a particular way sometimes might be more expensive compared to shaping it in, let's say, box kind of structures, right? So that is there, but the monetary thing comes more so in terms of the materials, their raw material costs, as well as the processing costs and things like that. But purely from the point of view of shape, any additional things other than the aerodynamics which would dictate the shape of an aircraft being different from that of a building, for that matter, or a bridge? Negate what? Yeah. Uh-huh. Mm-hmm. Mm-hmm. Yeah. So, whereas the building will also go through a series of temperature changes season to season, the range of temperature changes is much lesser compared to what an aircraft will go when it's flying from, let's say, the ground level to a higher altitude, or even more so for space vehicles and planetary exploration vehicles and things like that. So, range of properties for each material itself at different temperatures, and if they are joined to each other, there's a possibility that one could expand more compared to the other, etc. So you have to have appropriate joining technologies which will avoid or minimize the stresses coming out of those changes which are differential in the different kinds of materials. Anything else? Okay, so the primary implication of this in terms of the fact that the shape is not mostly dictated by the functionality of structure in terms of load bearing, but other functions like aerodynamics means that you have a more complex structure. An airfoil cross-section itself is a fairly complex structure, and in addition, of course, this is a straight wing, but typically for high-speed vehicles like supersonic, hypersonic vehicles, you'd have a delta wing or the sweep, and you could have a wash-in or a wash-out, which is essentially twist of the wing along the span. You could have a dihedral or anhedral in terms of how the wings are mounted to the fuselage. Again, where it is mounted on the either on the top of the fuselage, middle portion of the fuselage, or the bottom of the fuselage, or it could be strung through a set of truss structures, as was pointed out earlier, and you could have not just a single plane, monoplane that is, but a biplane where you have the wing broken up into two parts parallel to each other usually. So these kind of geometric choices make it a lot more complex. Of course, it's not that there are no complexities in terms of building shapes, but it's more from a point of view of aesthetics, and people want it to look unique or different in a particular way. And there could be certain functional requirements also which could bring in certain in terms of that. But here, even from the very primary function of whether an aircraft will fly or not, or it will fly efficiently enough for operations over a period of time, it depends on this choice of the shape, and usually those are fairly complex. The other aspect about the shape and even the size more particularly is in terms of the tolerances, the manufacturing technologies that are used. In the case of the beam, they might say, I want a beam which is of a square cross-section of 12 inches, and that if it is like, let's say, 12.1 inches or something, they wouldn't mind, it should be okay. But if something similar were to happen in the case of the aircraft, small percentage change could be a disaster in terms of the weight penalties that are incurred if it's more, or if it is less in terms of the possibility of a failure occurring much earlier than what is anticipated. Right? So the tolerances are low, which in turn means that we bring in the economic aspects that you talked about, because then the manufacturing processes have to be much more stringent, and therefore they could be costly. So one is the raw material itself is costly, because if it's a, let's say, a carbon fiber composite compared to a steel or concrete or whatever, it could be much more expensive. But at the same time, in terms of fabricating and manufacturing, it would be expensive. But over a period of time, as these new materials have become almost kind of a routinely used materials, the manufacturing techniques have also evolved quite a bit, and the costs have come down in terms of per unit volume or per unit mass. How much of cost we used to incur on a carbon fiber composite earlier compared to now is kind of drastically come down over the years. So these are things that evolve, but at the same time they evolve for the other kinds of structures also, but they have reached a certain level of optima because they have been around for so long. So there's not too much of an improvement. There are minor improvements every now and then. A new kind of a steel comes up, or there are certain additives to concrete or cement that comes up, and therefore you have slight improvements and things like that. But nothing like an entirely new material coming up in the case of the flight vehicles. And a lot of them have been used, there have been spin-offs from the aerospace industry to many other industries, sometimes completely not thought of at all. It's more of a serendipity that you would see that, let's say, for example, medical devices and things like that. There are huge amount of them being made, let's say, bone replacements and things like that. Many of those materials were originally invented for space applications, and eventually have applications on terrestrial applications as well. So then the other aspect is in terms of what kind of loads come up. You already mentioned thermal loads, the range of thermal loads being much more in the case of the aerospace structures compared to other structures, but also in terms of the time varying loads. So you could have certain impact loads, you could have certain vibrational loads, and those vibratory loads in particular, the frequency of vibration of the forcing function has a much wider range in the case of aerospace vehicles because of the kind of environment that it flies in. It could be the airflow itself, then the gusts and turbulence that could occur. It could be the engine, the flow through the engine, the exhaust, how it is coming out, and how the exhaust is being felt. Let's say if the engines were mounted on the wing or the fuselage, front fuselage, how is the stabilizer responding to that? How are the control surfaces on the stabilizers, like the rudder or the elevator or the ailerons, how are they responding to that? So those are the kinds of things that we have to be aware of. And so as a structural analyst, you will have to deal with multiple frequencies of loads that you would be observing, and you would see that it might be safe in certain range, but it may not be safe in the other range. So what changes do you need to make to the size, shape, and or choice of materials? So all these become the prerogative of analysts and designers eventually for flight vehicle structures. So we're continuing to distinguish what are the kinds of environments they fly in, what are the kinds of loads that result because of that kind of situation in which they fly, and then what are the implications in terms of the choices we make over the kind of materials and the kind of geometries we use as combinations, and also the joints. Next, joints is what I was talking about, the assemblage. So the number of parts of various types In other words, the various type of materials, various types of shapes. For example, in the aircraft wing, you could have the skin made out of a certain material, the spar made out of a certain material. Not only is there a difference between the choice of materials, but also in the shape. The skin is more like a shell-like structure. The spar is more like a beam-like structure. So one for one, from an analyst's point of view, because our focus in this course is going to be on structural analysis, it's going to be very difficult how you analyze a particular structure as a rod or a beam or a column or as a drive shaft, even for the same geometry. And then you go to a different geometry like this tabletop, you're talking of a plate. Or if it's curved like the airfoil top surface, the wings top surface, or the horizontal stabilizer or vertical stabilizer surfaces, you are seeing that they are highly curved and therefore shell-like structures. So the models that are typically used for shell-like structures and beam-like structures are very different from each other. You typically use for a shell or plate-like structure a two-dimensional model, which might work as good as a three-dimensional model if the appropriate choices are made. Similarly, in the case of a beam-like structure like this, just a one-dimensional model might be good enough. In other words, out of the spatial directions x1, x2, and x3 orthogonal to each other, you might just choose x1 alone, and that might be good enough. The variations with respect to x2 and x3 might be higher order effects. Only when you go to more detailed design of the various structures, you would try to get to those variations with x2 and x3 as well. But otherwise, just a one-dimensional model will do. But now you're attaching that one-dimensional stringer or a spar to a skin, which is a shell-like structure. For one, you're having a 2D model. For the other, you're having a 1D model. They speak very different languages. So they should not be lost in translation. So there has to be an appropriate communication, for which we typically, what we do is, we correlate it through the 3D, because eventually everything is 3D. All structures are three-dimensional in reality, just that for the modeling purposes, we model it as either these dimensionally reduced models of 2D or 1D. But there is a connectivity in terms of the math model. There are certain variables which are 3D variables, by which we mean they are functions of x1, x2, and x3. There are certain which are only 2D variables, only functions of, let's say, x2 and x1. In the case of a beam, there's lots of variables which are functions only of x1 alone. So those are 1D variables. But these 1D and 2D variables are functions of the 3D variables. And there could be certain special structures like this, which can, anyway, all structures can be modeled as 3D, but this particular shape can be modeled 3D, 2D, and 1D as well, because it's more like a strip, like a ruler that you have, a scale. So essentially what is happening is there are two small ratios over here. One is the thickness to the width is small. Similarly, the width to the length is also small. So if I want a very, very fast running model, computational model, I would model it as a 1D. But the accuracy will suffer to some extent. If I model it as 2D, yes, the accuracy will still suffer, but not as much. But it will be computationally a little more intensive. If I model it as 3D, it will be very, very accurate, but I might have to spend too much of computational time on that. So there are always choices that are made based on this, and how you derive a 2D or a 1D model from the original 3D model is also very important. So the kind of assumptions that you make, are they necessary? Are they even required at all? Because even without making those assumptions, if you are able to get to a theory, why even make those assumptions and restrict the what you think as the validity of the model? So these are the kinds of decisions that we will be talking about, and all of them are dictated by the challenges that the flight vehicle structures pose. But as you rightly pointed out, you have a lot of similarities as well. So the longer duration for which we have worked on civil engineering structures, there are certain takeaways for the aerospace structures, but the aerospace structures also have been around for more than a century now, so that their own modeling techniques and things like that have evolved so much that we no longer need to depend on that, but at the same time, we continue to evolve our modeling techniques for structural analysis so that they are more and more efficient, at the same time more and more accurate. Like what I pointed out last class also, there's always been this debate between accuracy and efficiency, because anyway computational hardware and software are improving so rapidly that should we at all worry about efficiency, because we have so much of brute force in terms of the computational power, in terms of the numerical capabilities that they have, why not go with an inefficient model? It doesn't work that way, because typically many of these could be used for design, which means there is an optimization which is done, which means many of these are going to be running iteratively. So even a small change in this running time for one run over a lot of runs will get accumulated to a huge change in terms of the time saving that you have. And for the industry, many a times the time saving is as important or even more important than saving money, because you take your product to market much faster, so you cover a much bigger market compared to your competitor. So that is the reason why people still are moving towards efficiency. Another example where you will see the real utility of greater efficiency is in terms of real-time health monitoring system, health and usage monitoring systems, which are becoming very common on flight vehicles, HUMS, health and usage monitoring systems, of which one part is SHM, or structural health monitoring. So these are real-time systems which will give to the pilot the health status of some of the primary structures, the wing of the aircraft or a rotor of a helicopter. If the pilot knows this a priori, that there is a crack developing somewhere and it's growing in a particular way, he or she can almost immediately make an emergency landing and avoid much larger fatalities or losses of even a monetary kind, can be minimized with the kind of maintenance schedules that can be incorporated. So keeping all that in mind, we will see how we will take this forward. Cost, yes, as you pointed out, yes, in the case of the building structures and civilian structures, cost plays a very, very critical role. Not that it does not play a role here. If and when we can save cost, it's as good. So in the case of the efficiency also I was talking about, even though we have very high performing hardware and software today which can run things much faster than what they used to even a couple of years earlier, but still any small increase in efficiency accumulates in a design process because of optimization, iterations involved. In the case of health monitoring systems, because you want real-time information and you can't afford to take a supercomputer on flight. The onboard flight computers are good, but they're quite capable, but not as capable as the best computers you have on land, which are much heavier or need certain special requirements like cooling and things like that, which might be the range of temperatures and pressures that they have to be kept in and things like that, which makes it a little more difficult. It's becoming even more so when you move on to quantum computing and things like that. But keeping all that aside, whether it is the efficiency that you're talking about or the economy that you're talking about, where you can save, if you can save, it's good enough. But just that in the aerospace industry, even a small change in the performance, I'll be willing to put in a lot more money into it as an industry, rather than for a building. If you're going to tell me this is going to lasting 200 years, it's going to last me 210 years, I might not care about it. I may not be willing to pay a few more crores to construct such a building. So that is the important thing, that you have to remember, that the choices depends upon the specific kind of applications that we have in the industry. But again, within that, there are so many different classes, like You might have housing which is of a particular kind for a particular class of the society, which are to be replicated in very large numbers over a longer period of time. So you might be much more thoughtful about the economy over there. If it's a one-off building, the pride of the nation, let us say you want to have something which kind of demonstrates the might of a particular country. It used to happen a lot in the past. You want to probably build a much more better looking building, even if that means a little more cost that is involved. So there are these outliers or exceptional cases, but what we are talking about as the primary differences here are in the run-of-the-mill case. The typical aircrafts that are used for, let's say, passenger aircraft, you could be making hundreds of those aircraft, or in the case of the houses, you might be making hundreds of thousands of houses of a similar kind of a design, and therefore these choices are going to be multiplied in terms of the time savings and cost savings, and therefore very, very critical. So remember, there are two choices you make. One is the material, the other is the geometry. Within the geometry, you make two choices again. One is the shaping, the other is the sizing. Because once you decide on a shape, I want to have a rectangular box, let us say, what is the width to height ratio? What is the thickness to width ratio? Is the thickness going to be constant or is it going to be changing? What is the thickness of the top and bottom? Is it going to be different from that on the left and the right? So these are the kinds of decisions that you have to make as well. Many cases you may not be so much of, so there may not be much of a nitpicking going over there. You might see the ease of making as the important criteria there. You might just go for a constant thickness all around that hollow structure. But depending upon where the stresses are more, where the susceptibility to different kinds of loads are there, you might want to make sure you have a little more reinforcement there in terms of more amount of material, a larger moment of inertia, whatever, if it wants to take bending, and things like that. Okay, so we will go into the specific quantities in terms of the geometry which are resisting different kinds of loads probably in the next week or the week after that. But essentially, that's where we are heading at, to how to make these choices. The choice of material, choice of geometry, within choice of geometry, the choice of the shape and the sizing, all of these. And many cases, so you will have multiple materials going on. So one is, of course, the joining technologies, but also the compatibility of those two materials. They should not be chemically reacting with each other. As you were pointing out in terms of the difference in temperatures, they might have different coefficients of expansion, or many other things which could result in higher stresses than what it was designed for. So the joining technology is not just about the joining alone, but also in the service life, what kind of environmental changes that it could go through, what kind of loading ranges that it is encountering. Based on all of that, the joining technologies also have to be appropriately chosen. Most importantly, they have to be compatible with the two kinds of materials that they are trying to join. Okay, are there any questions on what we have discussed so far? Yeah. Different types of what concerns?
Safety concerns.
Yeah, yeah, yeah.
So, like, the safety concerns for like a building might be different than like an aircraft and stuff, and like safety concerns between different types of aircraft, like a military aircraft versus like a commercial aircraft would be different as well.
Excellent point that you brought out. Yes. In fact, there are differences. In fact, there are differences not only in terms of the specific choices that we make, but even the paradigm itself, in terms of the philosophy itself. We will see shortly. There are philosophies like fail-safe, safe life, and damage-tolerant kind of structures. So what used to be done in the past are in terms of fail-safe structures. You make it so strong that it will never fail. But then the weight penalty is much, much larger in the case of the aircraft, so you would not want that. We were just a few minutes back, we were discussing the possibility of having a biplane instead of a monoplane, that is the wing being broken up into two parts there's a upper part of the wing and a bottom part of the wing, instead of one large surface wing, which is called as a monoplane, which is a more common choice. Instead you make there. So if one of them fails, you might still have some lift sustaining this, and maybe it will drop at a fast rate, but at least it may not crash in a fatal sense. So there's a redundancy that is built in. So you have a backup plan. If a structure A fails, there is a structure B which can share that load, and probably it may not be able to fly the entire flight plan that was original, but it could be an emergency landing in a closer airport or something like that, and you eventually save. So there are those kinds of possibilities. So one is you have backups. The other is you make it the individual item so strong. In the case of the landing gear, for example, you do not have a backup. So you have those tricycle or whatever 3 landing gears, but each of them doesn't have a backup, in the sense that those structures, for example, that's one of the few cases where we have not done away with steel. We continue to use steel to a large extent, a lot of these landing gears, undercarriage structures. The reason is that we are looking at a fail-safe kind of a design. So you're trying to see that you're ensuring that it is so strong that even in the worst kind of scenario, it will still survive. So that is the kind of philosophy or paradigm with which we build them. Whereas there are certain other structures where we are willing to let it go. If it fails, there is another backup for it, which will survive for at least a part of the time that we require. So, and then again, the third, which is becoming much more common in the case of composite structures, is neither fail-safe nor safe life, but damage-tolerant kind of a design paradigm, where we are saying that is this such that it can tolerate the damage. It can get damaged. The damage can get initiated, but it is growing so slowly that the aircraft can still be landed, and then a repair schedule can be taken up, so that before it flies again, takes off again, you would have that rectified or replaced depending upon the severity of the damage that is involved. So also in terms of how fast the damage is growing and things like that. So all of this will have to be taken into account in doing that. So I'm glad you brought up that point. Yeah, so safety consideration is important. Anything else? Yeah, okay, so this is as far as what we wanted to, cost relatively less critical. Yeah, I would be using this symbol. Many of you might have encountered it earlier also, if and only if. So if I put a double F there, it means if and only if. So it's both a necessary and a sufficient condition, in other words, what we call in mathematics, okay? And is warranted by performance gains. Yeah. So here, because you're in India, I want to take advantage of that situation that you are here. There is an aerospace museum that is there in Bangalore, not very far from here. So I would urge you to kind of visit that. It's a aerospace heritage center and museum. It's run by the Hindustan Aeronautics Limited, HAL, which is one of the pioneering aircraft manufacturing companies in India, very well known for its helicopters. It has manufactured over a long period of time, but it has also been serving the Indian military, the armed forces, both the Air Force as well as the Army and Navy requirements for aircraft and aircraft trainers and things like that. So it has been making a few aircraft. You would have seen couple of aircraft outside as well, trainer aircraft that were also made by HAL, and HAL runs this particular museum. Bangalore, fortunately for us, is the aerospace capital of India. This is where it all began, and this particular department has a history which is parallel to HAL, that is the Hindustan Aeronautics Limited. In fact, HAL was started in 1942, and this Department of Aerospace Engineering in IISc was started in 1943. Because as soon as they started HAL, they found severe shortage of the human resources, and therefore they wanted something which is specifically trained towards aerospace programs like that. And we have been kind of the go-to source for the aerospace industry, not only HAL, but eventually now we have the Airbus Engineering Center in India, which has more than 3,300, 3,500 engineers. The Boeing company from the US has huge investments in Bangalore, thousands of engineers there as well. Engine companies like GE and Pratt & Whitney, Rolls-Royce have all had very big openings over here. And many of our students work there. Of course, the Indian Space Research Organization, or ISRO, is very, very popular world over for the kind of performances that it has given with much lesser cost compared to many other space agencies like NASA and ESA and things like that. So many of their employees are also graduates from IISc, this department. Similarly, we have the Defense Research and Development Organization, or DRDO, which has a lot of labs which make aircraft for the, or design aircraft which are military in nature, also drones and things like that, eventually which gets manufactured by HAL, but the primary design is done there, the rockets, the missiles, and things like that. The missile program is very big in DRDO. So it's kind of, this is like the cradle, this department is the cradle of the aerospace industry in India, and many of them are still attached to this department in terms of having certain projects and collaborative research, and some designs are also done jointly by my colleagues and me along with them. So there has been a lot of interaction going that way, but unfortunately many of these things are not known around the world. So now that you're here, and anyway you're already aware of the aerospace supremacy of the US around the world by a large margin, but there are things happening in other parts of the world as well, and lots of components and structures in particular, because we are interested in structural analysis, are supplied from so-called tier 1, tier 2 partners of Boeing, Airbus, etc., Bell Helicopters also, from Bangalore and many other surrounding cities. And almost all Boeing aircraft or Airbus aircraft have at least a few parts which are made in India. So it's important that you're aware of how the aerospace industry works. So these big giants like Boeing or Airbus come up with a design, but eventually the components are made by a lot of different partners all around the world, and eventually they are all brought together to particular locations and assembled together. So that is how this aerospace industry works. And so when you understand the aerospace industry, it's not just these big companies, but their partners who are tiered in terms of what they contribute, how big a component they contribute. Somebody might be contributing an entire wing, typically like a tier 1 partner. They could be contributing spars and or stringers and parts, the wing skins, etc., panels for that. So that could be a tier 2 or tier 3 partner, and so on and so forth. So depending upon how how complicated those design elements are and manufacturing processes are, you get different levels, and also in terms of the quality, and which are all evolving things. A company which is tier 2 partner today might become a tier 1 partner in a few years based on how they have been delivering over a period of time. So keeping that in mind, and since you have already done a course on materials and you have been exposed to composites, etc., so this assignment will be about this is a picture that you will see in many of the aircraft magazines, and also Jane's All the World's Aircraft and things like that. Soft copy versions of which are also available. You could probably use VPN to access your library to see some of these things as well. But and there's a lot of material on the internet itself. There's also a magazine called Flight International that many of you might have taken a look at, they have these kinds of cutout pictures. This is of course very simple cutout, but much more complicated cutouts which take off the skin from a part of the aircraft just to show you the skeletal structure, how complicated it is, and color coding to refer to which different materials are used at different locations. A darker shade could be a particular material, a lighter shade could be a different material, and so on and so forth, and you typically will have tags going on with it. So at this stage, obviously, you have a certain level of knowledge towards this. Maybe some things you have even read out of interest or whatever, but I want you to take it to the next level in terms of trying to see, be prepared for what is going to come in this course. Because in this course, we're not going to make too much of these choices and things like that. We are going to, given a particular aircraft structure, how do we go about analyzing that? That's what our focus is primarily going to be on most of the remaining classes. But it's important for you, as I said in the last class also, to have this bigger picture where you understand where it goes, why it goes there, why this particular material is used at that particular location and not at some other location. What is the particular property of this material or set of properties of this material which makes it so much more suitable for this application? Okay, or it might be so costly that it is used only in critical portions and it's not used in certain other portions. But you have to make that judgment or speculate on all of these, and you have to give appropriate references for that. So that's what is going to be the assignment over here. So once, like last time, it will be a group presentation. You'll all present it together. So you can probably split this assignment in whatever way you feel comfortable or convenient, and take up a few aircraft which are more recent aircraft made in India. The light utility helicopter, that is LUH. The light combat helicopter, which is also made by HAL. Then we have an entity called the National Aerospace Laboratories, which is part of Council for Scientific and Industrial Research, or CSIR, which makes all composite aircraft like Saras and Hansa, much smaller aircraft, but essentially technology demonstrators, but also having certain applications and certain consumer targets for that. So they've been around for a while as well. Then I was talking to you about ISRO, the Indian Space Research Organization. They have certain satellite launch vehicles which they use to launch not only Indian satellites, but a lot of satellites for other countries as well. It's a huge market, the satellite launch market, and India is one of the fastest growing markets as far as the launch industry is concerned, because we can launch some of these vehicles have been designed in such a way, and their flight paths are optimized in such a way that they can carry hundreds of satellites at a time and put it in multiple kinds of orbits and things like that. So many such challenging tasks have already been performed, all the way from nano satellites to much heavier satellites in the geostationary satellite launch vehicle. This is the Polar satellite launch vehicle. So here you have also a cryogenic stage. So you would have, for the cryogenic stage, the kind of temperature issues that, because it's like liquid fuel that you're having, or a liquid propellant is essentially, and that is going to mean the kind of containers that you have are going to be much more stringent in their requirements. For example, liquid hydrogen could be kind of volatile, and you need appropriate protection. So what kind of materials are used around that? And some of these could be proprietary data. You may not be able to access all of them, but how much ever you can access. There is quite some information in the free literature as well. So based on that, I would like you to come up with what are the types of composites in particular, but also other materials like aluminum alloy, titanium alloy, the steels, etc. Where, for example, I was talking about the landing gears being made out of steel. Why are they so, and things like that. I just want you guys to come up with that for specific aircraft rather than generically talking about like what I did for all kinds of aircraft, right? So yeah, I think that should do. There are also the other military aircraft for which you might not find too much of an information like the light combat aircraft, etc. But here you see the percentage of different materials that are used, and slowly you see that carbon fiber composites percentage is increasing quite a bit. With the Boeing's Dreamliner and also the Airbus A350 have more than 50% of composites already by volume. By mass it will be even more. So it is in terms of percentage it will be even more because of their lower densities. So keeping all that in mind, you would also see in all of this, whatever I have put up here is from the internet, just internet searches that I have accessed all this. You could access much more than this. But more than what is used where, I want the reason, okay? So this is the most important critical part. I want you to answer why, okay? It may not be clearly specified there, but can you speculate? Because you have had a course on materials. Now you know this particular material is used in a particular location on the aircraft, what kind of an aircraft it is, what kind of loads it is typically susceptible to, not in terms of the magnitudes and things like that, but overall comparatively, relatively speaking. And therefore, because that is the dominant kind of loading, that is the therefore this is the dominant kind of property that I want, and therefore this material can give me that property, therefore I choose this material for this. So that is how the designer would have gone about it. You don't know exactly what all went into it. There could be a lot of economics, there could be a lot of geopolitics in terms of the availability or accessibility of certain materials which are not made in India, let us say. Are they coming from other countries or not? Do they have certain embargoes? Because they could be dual use kind of materials, dual use technologies where you can use the same thing for military purposes as well. So some countries may not be willing to share those materials, even though it makes a huge business sense for them. So leave those things aside. I do not want you to overly complicate with that. If you can get information on that, access that, well and good. Once again, you could utilize your AI resources and things like that. So that is something that is going to be valid for all the assignments throughout this course. But whatever resources that you can lay your hands on, try to do that, and we will try to once you make the presentation and give out the reasons, I will also come in and say, probably add to your reasons or argue with you about some of the reasons, etc. Maybe you have a point there and we can try and learn from each other. So that's what this assignment is about. Do you have any questions on this? Yeah, okay. So let's move on. Okay, so the next topic is in terms of the criteria to select and also to handle, not materials or geometries that we are talking about for aerospace structure, but what topics we are going to study as part of this course. Okay, because structural analysis is a huge ocean because it's been around for so long. So much of development has taken place in terms of different kinds of methodologies, different kinds of applications, and different kinds of interpretation of the results, etc. So we need to be a little more focused in terms of which topics we can probably cover within the short period of time we have in the remaining 18 classes. So we want to see which topics we choose, how we handle those topics, and also are there certain ways in which we can classify aerospace structures. These are the, we were already talking of shell-like, beam-like, etc. That is one way of classifying. There are many other reasons or bases for classification. We will also look at some of those bases as well. So as a mnemonic, we can think of it as 6 kinds of topics, all of which start with the letter F, the fundamentals, and then 5 Fs. The fundamentals, of course, is like the building the foundation for whatever we are going to learn, part of which we have already done in the today's class and the previous class this week. But we will try to do a little more in terms of understanding the fundamentals. Once we are there, we will bring in 5 more Fs, which are very, very critical. We may not be able to do justice to all of them, but nonetheless, the importance of all of them, almost equal importance, has to be understood and appreciated, which is why I am just cursorily going through over them right now. So the fundamentals, of course, will involve, we will review some of that from your deformable bodies course, for example, or the materials course as well. There involves the materials. Then it involves a particular way in which most of these materials behave, that is their elastic nature, that is given a stress, there is a unique strain, given a strain, there is a unique stress. That's a mathematical way of defining elasticity. In terms of the experimental way of looking at it is that you load it, it goes to a particular deformed configuration. You remove the load in a gradual fashion again, it comes back to its original shape. So that is how we observe it as an experimentalist. But purely from a mathematical point of view, it's a unique function between the stress and the strain. So in other words, a particular stress field cannot have any other strain field. It has to have only one particular strain field. Similarly, given a strain field distribution throughout, which means that as a function of both space and time, then there is going to be only one stress field which is going to come out of that. Then the fundamentals also include failure, but failure has its own aspects, which will also be part of that Fs that we are going to be talking about. But then whatever failure models that you have already looked at, we will try to revise that. Then we will look at the 2 major types of structures that you can find almost everywhere on every flight vehicle structures. Every component that you take, more often than not, is going to be either a beam or a shell. Okay, so why is it so? What is the purpose of making beam or shell-like structures? Where beams, where shells? Just like in that assignment you are talking about, where a particular material, where some other material, there should be a reason for that. Similarly, where a beam, where a shell, what kinds of beams, what kinds of shells, etc. And we will use the word beam for one-dimensional structures, anything which is long like this, irrespective of whether it is a rod, in which case it is a tensile load that it is subjected to, or it's a column, in which case it's subjected to a compressive load, or it could be a torque tube or a shaft where you're subjecting it to torsion, or it could be a beam in the classical sense where you're subjecting it to flexure, that is bending in any one of the directions, right? So, but in essence, they are all one-dimensional structure. In other words, the length is much, much larger compared to the cross-sectional dimensions, be it the width or the height. They are much, much smaller compared to the length. And therefore, there are certain simplifications that you can make in the 3D model when you're using it as a 1D model. So we will include extension, both positive and negative, tension and compression, that is, making it rod as well as column. Then bending, as I said, in which case it is a classic beam, but we will call it as a generalized beam which takes all these kinds of loadings. Then there is torsion, and then there is shear as well. That means you're applying a load which is not axial like tension or compression, but perpendicular to that. In other words, tangential to the cross section in any one of these directions. That is essentially a shearing kind of a load. So you will see that, for example, the shells are really good at taking those shear, and whereas the beams are good at taking these 3. And as a combination, you try to use these. And sometimes, almost always, the torsion results predominantly in shear. Therefore, the kind of torque tubes that you build might be hollow structures, which are essentially shell-like structures as well, even though they might be long. So, in other words, a structure like this, which can be, as I said, can be modeled both as a 1D beam as well as a 2D shell. So we will see examples of structures like that. So it's a very, very interesting zoo of animals that you have in terms of the aircraft components, structural components. But we can, with the classification that we are going to do, bucket them in various categories and see which is the most efficient way of handling them in terms of an analysis, mathematical analysis. So, of course, talking of the 5 Fs, the first of them is the fiber reinforced plastics. Of course, composites are a huge body of materials. Typically, when you're looking at the classical materials, you used to have metallic alloys, you used to have plastics, you used to have ceramics. But then once composites came in, of course, nature has had its composites in the form of bones and wood, etc., for a long period of time. But we're talking of engineered synthetic structural composites on engineering structures like aircraft. The predominant matrix has been plastics. So, and the fiber that reinforces it could be of many of these three. That is, it could be typically a carbon fiber is a ceramic kind of a fiber, or you could have even a plastic fiber in a plastic matrix, so aramid fibers in an aramid matrix, for example. Or you could have metallic fibers as well, especially for higher temperature applications. You could have that. And also the matrix choice is more often than not based on the range of temperatures that is being considered for a particular application. So structural components which will go into the engine, in particular, let's say as we go from the compressor stages to the combustion chamber and the turbine and the exhaust, the temperature is going to keep on increasing. Therefore, you need more and more high temperature capable materials. So you would not be able to use FRPs, for example, because plastics cannot take beyond a certain level of temperature. But within plastics, there is a certain range in terms of thermosets and thermoplastics, etc. Different kinds of thermosets and thermoplastics are capable of different temperature ranges. But when you want to go to even higher temperatures, you typically go for metal matrix composites. So where it could be, let's say, you could have a silicon carbide fiber, which is a ceramic fiber embedded in an aluminum alloy or a titanium alloy. So you can handle higher temperature than plastics can handle. Then you go for ceramic matrix composites. There are also, for even higher temperatures, like for example, re-entry vehicles, when vehicles from space are coming back, like the shuttle, there are certain portions which get really, really hot because of the aerodynamic heating. And there you need, probably if you're looking at composites, carbon-carbon composites, where the matrix is also carbon, as much as the fiber is a carbon. So those kinds of possibilities are there, but for most conventional aircraft, etc., FRPs have been the dominant composite material which have been used, plastic material, in particular epoxy as a matrix, though there are various versions of epoxies itself and a few other plastics also used depending upon certain nuances of requirements in certain applications. So it's a huge amount of weight saving. Typically, of course, different aircrafts and different kinds of design philosophies will result in a range of weight savings, but quite frequently you find of the order of 35% structural weight savings. So in other words, as an aircraft, you are allotted about 20 to 25% weight for the structure. The rest goes for the fuel, the payload, and the various control systems and things like that. So many other requirements are there. The structural people get about 20-25% at the most. So which means that you have to utilize that in the best possible way, most efficient way. If you're able to utilize even lesser percentage of the overall gross weight of the aircraft than that, even better, because that could mean probably taking more fuel, therefore having a larger range, or it could mean taking more passengers, which could be more lucrative for the airline which is going to purchase and run that particular aircraft. Or it could be with the same amount of fuel and the same amount of passengers, but overall lighter aircraft which flies much faster or has a better performance and other performance parameters. So from point A to point B, you're probably able to go much more quickly. So many other possibilities are there. So you might think that you're only saving it from a structural point of view, but no, it has repercussions throughout the entire aircraft design in terms of what are the advantages that seeps in for the overall design, and which is the reason why it's important. So it's widely used, as I said, in the case of the B787 or A350, it's about 50% by weight and 70% by volume in both these aircraft. And of course, these are substantially different, the fiber reinforced plastics, compared to traditional metallic structures in terms of being anisotropic instead of isotropic. And also multiple materials at a very low length scale, and therefore interfaces between those materials. Therefore, the possibility of the interfaces failing. For example, there could be a debonding between the fiber and the matrix. There could be a delamination between two layers of the composite. There could be a fiber breakage. There could be a matrix cracking. All of these one could lead to the other, and it could be fairly complicated mechanism of damage, initiation and growth. So we have to be able to handle that even before it gets damaged. Even the healthy composite structure compared to a healthy metallic alloy structure is quite difficult to deal with, because you are going to be talking about anisotropy, which means properties are going to be different in different directions. And you're going to be talking of heterogeneity, which means that properties are different at different locations. The fiber properties are vastly different from the matrix properties, and they change over from fiber to matrix within a few microns. So which means that there's going to be changing so continuously. So, but there are ways that have been very, very ingeniously invented long ago, in terms of how to handle these complications of anisotropy and heterogeneity. We will see, you probably have had a glance of some of these things already, but we will see how we do it typically, and we will see that those seemingly complex problems are actually quite easily handled and almost on a routine basis today, not only by industry but academic institutions too. But nonetheless, because of the extensive usage that is happening with them, you have to have an introduction to them. So one of those 5 F's that we want is FRP. There's no doubt we cannot leave it out even from an undergraduate course or introductory undergraduate course. All of these F's have to be given at least some kind of a cursory overlook, and which is what we will do as far as FRPs are concerned. The second aspect we will give even lesser amount of attention to, but it doesn't mean that it's not important. It's as important, is fracture mechanics. So as I was talking to you about in the composites, the various kinds of damages, one leading to the other. Even in metals, metallic alloys, you will see that there's a lot of complication as far as the fracture mechanics is concerned, both in terms of the initiation and growth of cracks, etc. So it's an important tool. I was talking to you about, other than fail safe and safe life, there is a particular technique or philosophy that we use in designing structures, that is damage tolerant structures. So for composite structure damage tolerance, the understanding of fracture mechanics is very important. Though fracture mechanics as a subject has been around for a long period of time, most of the work has been historically about metals. Only in the last decade or couple of decades we have had models for fracture mechanics for composites, but none of them are really as reliable as the fracture mechanics models we had for metals. So still a lot more research and work needs to be done in this particular area. And it's not only for, this is of interest, fracture mechanics is not only of interest for very old aircraft which are so old that their parts have started failing, what we call as aging flight vehicle structures, but it's also important for even new designs where you don't have a deterministic model which works well enough anymore. What do we mean by a deterministic model? I say I have an aluminum alloy, I know its Young's modulus, I know its yield strength, I know its ultimate strength, I know its coefficient of thermal expansion, and I use those numbers to design. But eventually the component behaves as if those numbers were all wrong. Why? Because there is a variation in those properties. Even though for as a datum we take certain specific values for these quantities, within a lot you will see a lot of difference between it's the same lot which has been manufactured by the same company over a same period of time and has been supplied to you. But if you make specimen from one end of the lot and another end of the lot, especially with a composite, you are going to see very, very different results for the strengths, for the stiffnesses, etc. In other words, there's a lot of scatter. So you cannot deal with specific numbers for many of these material properties. You have to have probability density distribution functions for each one of these. It varies with a certain mean value, certain standard deviation, and are you able to input that as your Young's modulus, or another distribution for strength, another distribution based on the manufacturing techniques for the tolerance, and therefore the sizing of these materials. There could be a slight variation, and some of these can deteriorate during the service life. So during the service life, as it gets used, as it gets loaded, unloaded, especially in that kind of a fatigue kind of an environment, over a period of time, the strengths can come down, the stiffnesses can come down. All of this can be accounted for in a probability density distribution function, and you give that as inputs, and then you get the output in terms of the overall design parameters, how do I want to size it, etc. So then it becomes much, much more reliable. In the case of a linear model, when everything works linearly, proportionally, it's very easy, because then the principle of superposition will work, and therefore you can very easily convert your deterministic model to a non-deterministic model. Just wherever there is this function, you just substitute it by the function for the PDF, and then you essentially end up with another PDF for the end results. But how the PDF initially looks and finally looks might be very, very similar for a linear kind of a model, but most of the reality, the way these materials behave, the way the aerodynamic loads occur, etc., all of these CFD models and CSD models, that is computational structural dynamics models, are all highly nonlinear, and they are coupled. Fluid structure interaction problems become so enormously, humongously complicated, and you do need to have an understanding of how you're going to do these kinds of non-deterministic techniques, how you're going to apply for such kinds of problems. So it's highly desirable for us as engineers to get an exposure to it. In a course like this, we will not actually get into the nitty-gritties of it in terms of how exactly it is done, but it's a question of being aware of this. Irrespective of whether we are going to be structures engineers or not structural engineers, we might get into aerodynamics or propulsion or controls and navigation guidance, it doesn't matter, but we have to be aware of all these aspects of structures, because as a design team, you'll be interacting with people from this background, and when they say something, it could have implications in certain decisions that you are making, and therefore it's important that we are taken into confidence, and they are taken into confidence by our decisions as well. So the third F that we are going to be dealing with, other than FRP and fracture mechanics, apart from fundamentals already, is fatigue. And briefly mentioned, this is essentially a time varying load. Something which fails at a particular stress value, if it's a static load which is constant at all the time, but if that same load were to be changing with respect to time, then the failure would occur at a much lower stress. So in other words, the strength drops based on whether it is a static load or it is a dynamically varying load, and it could vary with the frequencies of the loading and number of cycles that it goes through, etc., and what is the maximum value in that cycle of the stress, the minimum value of the cycle, what is the datum, etc., apart from the frequency. All of these can have implications on the strength. So one is the strength and stiffness are changing because even here, because of the anisotropy of the material in different directions. Because of the heterogeneity, it's changing from location to location. Then because of the variations in the properties of fabricating those materials, you're going to have from lot to lot, that's going to change, and therefore the properties are going to be not fixed values, but changing distributions rather. So then now we are coming and saying that you're talking about fatigue, and that can cause further reduction depending upon the kind of load cycles that it goes through, this particular material goes through. So that's going to be a critical aspect as far as the durability of that composite structure or any structure, metallic structure also, which is going to be loaded dynamically, and that therefore that is important as well. So maybe I can finish those 5 elements. So Yeah, fourth F is the finite element method. That's almost become like the bread and butter for a lot of structural engineers over a long period of time. So the finite element methods, there are lots of commercial codes like Nastran, ANSYS, Abacus, etc. And many of these are standardly used in the industry. But many of the big companies like Airbus or Boeing have their own proprietary codes as well, or subroutines that go along with this, user subroutines, and they mix and match them along with the basic code. And many of these companies, like for example Abacus, has benefited a lot by what Airbus has done, for example. So there's a feedback going on from the users to the company, and even they share some of this knowledge, so that some of the newer versions of Abacus will have a lot of inputs from the aerospace companies, Airbus in particular. So the finite element method has become almost the common denominator in terms of how structural analysis is done. So which is why when we are going to be talking about, you had a question? Yeah. When we are going to be talking about how we are going to do the structural analysis, this particular course, the way it was traditionally done is a lot of problem solving, where we do it for very, very simplified structures for which we can do hand calculations, etc. Yes, it's good in order to get a feel for the problem, but that's definitely not the way in which the industry works, and which is why many of the industries feel that graduates who go through this kind of an education eventually are not suitable. Does that mean we are going to be training them in software? Absolutely not, because it's important that we understand the physics, the math behind it, so that when something doesn't work, you know how to tweak it and how to make it work, to choose the appropriate kinds of inputs, the appropriate kinds of outputs, which is again very, very similar to what you're going to do as post-processing of that output, which is again very similar to what you're doing with the LLMs now in terms of the prompts. The prompts you give, the response it gives, you go back and deal with the response, and you of course set the parameters for this, like temperature, etc., to for these LLMs, to make sure that they are giving you the kind of complexity that you are desiring, along with the kind of creativity that you're desiring as well. For example, if you're going to be asking it to write a poem, you would let the choice of temperature, etc., be such that it becomes as creative as possible. It gives it much more leeway. Whereas it's a very, very rigorous math problem, you don't want it to kind of become too hallucinative, and so you try to appropriately give the temperature for that. So essentially what we are saying is that the same kind of a thing applies for the finite element method as well, in terms of how you're going to be post-processing this data, how you're going to be giving the inputs, what type of models, because there are various models that are possible within each one of these software for different structures, and when you're dealing with a much more complex structure, which is a combination of many different kinds of structural components, you might have different models for each one of them, how you're going to interface them with each other. When damage is also included, there could be what are known as cohesive zone models at those interfaces where damage is initiating and propagating, what kind of elements you choose for that, etc. So those are all going to be the kinds of things that we will take a very cursory look at to understand how it is being done currently, and therefore what we need to be ready with. So many simplified ad hoc techniques. Ad hoc is an adjective that we will use quite often to refer to something that is valid for a specific case. It's a Latin phrase which essentially means that yes, it's a valid assumption that you're making, but it's valid in a very, very narrow class of problems. Then you start applying it to a broader class of problems, obviously everything goes for a toss. Right? So you do not want to get into that kind of a situation. You need to understand how to broaden the model's validity, making it much more robust by ensuring that the assumptions that you're making are valid and indeed are necessary for the derivation to take place. So that's why those many simplified ad hoc techniques which used to be there in many books, many textbooks, even for written by some really well-meaning authors over a long period of time, but no longer of great utility from the perspective of the employers eventually. Even if you're going to be in academia and going to do research in this, for teaching, yes, if you're going to be continuing the way your advisor was teaching, you want to continue in the same methodology, fine, well and good, that's good enough. But if you're going to be doing cutting edge research, you're going to be working with the industry as well. Just like your students are going to be employees of the industry, you might be doing consultancies, you might be doing collaborative research with other colleagues and with the industry, also coming in as multiple partners. In all those situations, you have to be aware how they do it, and you have to give something that is going to be of benefit for them in the future. They are already doing something that is useful for them today. Academics, the way we contribute to the industry through our research is by contributing something which will be useful for them 5 to 10 years down the line. So are we able to work on those methodologies? Unless and until we understand how they're working today, how are we going to help them out with something futuristic kind of a problem? So that is essentially what that is, the fourth one. So I think we will take it forward from here in the next class because it's past 4:15. So the fourth F and also the fifth F we will cover at the beginning of next class. So I already gave you the homework so that you can present at the beginning of Monday's class, and then we will continue with this. Thank you.